evening. So thanks very much for asking me to talk. It's nice to be invited. This is a patch of ground that's sort of much cherished. The River Itchen has got oodles of national and international designations, protections, environmental, for its kind of very beautiful gin clear fish jumping water. It's also the source of quite a lot of water for public water supply at the moment, and agriculture and industry, and there is a bit of a sort of ongoing conflict there. So that's largely what I'll be talking about. This is a patch where I've worked, as Nigel says, for the last 20 years or so, and the people who paid for all of that are the Environment Agency, Southern Water and South East Water mostly. Lots of lovely people: Alison Matthews, Mike Packman, back in the day Paul Younger was an external peer reviewer, Jane Dottry just chipped in with loads of ideas, and lots of my colleagues over the years, Tim and Stefan and Amy and Rachel and Shamek and all sorts of other people. So thank you to all of them, and particularly to the guru of chalk, Professor Rory Mortimer, who's lots of strat and stuff ideas. You'll see him coming in this presentation, but you can blame me for all of the comments and conclusions. You can't blame any of them. So the stuff that I'm going to talk about, I have a reputation for trying to fit far too many slides into presentations, which I shall thoroughly fulfill, I'm afraid. Because you're a bunch of geologists, not all of you hydros, I'm going to start off talking about the solid geology, some of the structure, looking at the flowing horizon things. I'll touch a little bit on what groundwater levels and river flows sort of tell us about things. I love a bit of time series data analysis and maps and contours and things. The superficial mapping of the geology is also really helpful for understanding the hydrogeology because of the history of what happened in the Paleogene particularly. There'll be a bit of a summary of kind of what I think is going on hydrogeologically, and then a swift sort of talk through how you turn that into a numerical groundwater model. And then I'm going to focus on a particular corner of it where there'll be a bit of talk about how particular abstractions actually end up translating from being pumped out of the ground to being impacts on the river flows, which is quite interesting and wonderful, and it illustrates basically what groundwater storage can do in areas like headwater catchments of the chalk generally. And basically we have over the years used that groundwater storage to help us supply people with water and also to keep the environment going through droughts. There is a bit of a challenge to a lot of this at the moment, something called the Environmental Ambition Challenge, where there's a desire to kind of meet river flow targets everywhere, and a lot of pressure on reducing groundwater abstraction associated with that. So I'm going to talk a bit about that. I'm going to look really a little bit to the future about what might happen in terms of changing flows anyway, regardless of abstractions, with climate change and droughts. And at the end, I'm finishing with a quick blast on whether or not we have, in fact, somewhere along the line lost our balance a little bit, with a bit of a plea to kind of save our aquifers, and then some questions and answers. So hopefully I'll get through that in an hour and leave a good half an hour or whatever to chat through it. So you'll have gathered there's a bit of a spectrum I'm taking you through. There's some interesting geoscience. There's a little bit of shocking but true stuff towards the end, and then it kind of ends up with a bit of a grumpy polemic. But you have been warned. There we are. You can blame me for it. So starting out with where this sort of area of interest is. So the River Itchen and the River Test are obviously in Hampshire. They flow into your beloved Solent via Southampton Water. The focus of the modelling study is a bit broader than that. It sort of includes a bit of an overlap with the Wessex Basin model to the west. It covers also rivers that drain the chalk outcrop off and flow eventually into the Thames, both to the east and the north. So that's the area of ground we're talking about. The chalk obviously dips underneath the London clay, both to the north and to the south, into the London Basin, and then down into the Solent, etc. So that's the patch. Geologically, solid geologically, this is the first of Rory's pictures. The chalk was obviously laid down in very quiet conditions, and has interbedded within it, throughout it, a series of flinty hard ground, some of them tabular, some of them sort of lenticular, but reasonably regionally pervasive often. And being flint and therefore siliceous, they're not so dissolvable as the rest of the chalk. And so as a systematic thing, recharge will often percolate its way down through the chalk, get stuck on one of these, and then flow off down dip. So these things tend to both partly reduce flow through them and also promote flow on top of them in the ground, as do horizons like marls and mudstones and things. So the Plenus marls is a famous one. So these horizons tend to end up often where you get springs coming out of the ground. It's because one of these horizons is coming to the surface. And when the chalk gets folded as well, because those horizons are different from an engineering point of view, they tend to be a focus of fracturing, and again, that promotes the development of flow across the top of them in particular. So we know that there are some horizons that are typically associated with regional flow into boreholes and things over quite wide areas. The Whitway rock, the Bar End hard grounds, etc., the chalk rock, Melbourne rock. And that's so we wanted to start off understanding how those are distributed, because obviously the whole chalk is folded in a series of relatively shallow sort of east-west trending axis folds. And the notion is, this is BGS mapping, that there's preferential down dip flow and a concentration of groundwater flow, and indeed recharge within syncline areas in particular. So in order to understand that, we did some very simple creation of a geological model, a structural model, where we took Rory's kind of regional understanding of the typical thicknesses of these formations, which can be reasonably well correlated using geophysics, etc., over fairly wide areas. And we simplified that into there's a lot of outcrop in this area of the New Haven chalk, which is relatively high up, and that interface between the New Haven and the Seaford chalk. So we recognize that by combining the topographic elevation and the lines of where that contact is, you can get a reasonably good idea of what the structure of that surface might be. Obviously, that's not present everywhere. So in some places, we've just used some very simple uniform thickness assumptions about the underlying formations or the overlying formations in order to be able to extend the coverage of that surface over the whole region. So this New Haven chalk is the darker green, and you can see there's a lot of places where there's that contact, which you can then intersect with LiDAR-based topography stuff. So you've got a lot of points that we've then created along that contact and along the other formation contacts, which you can add or take meters off to work out where the New Haven chalk would be, if you like, if it hadn't been eroded out. To that, we add some a little bit of controls down the center lines, axes of synclines, and off towards the north and south as the chalk dips off to depth. And that extends enough coverage that we can work out effectively where that reference horizon, the base of the New Haven chalk, would be across the whole of the model area. And from that, you can immediately see that there are some lines of anticlines and synclines, which are really important for the kind of the flow of groundwater. They influence the topography to start off with, because these will probably also tend to be areas of higher ground. And the interaction between that structure and the surface drainage, which now often cuts across it or may be parallel with it, helps to explain quite a lot of the distribution of flow in the rivers and things. So in order to work out what flowing horizons might be important, we looked at boreholes and also locations where there is, for example, on the superficial map, a transition from valley head to alluvium, which is often where the perennial head of these winterborne streams are. We looked at where there are cress beds and fish farms, which are often located, again, where there's an outflow from the groundwater system, and in many cases they're located where they are because of these flowing horizons coming to the surface. Various people had looked at, studied boreholes and looked at geophysical logs or flow logs in boreholes to see which horizons have you got water coming into these boreholes, and some of the public water supply boreholes as well, obviously because they're a focus of, you know, where we get our water from. There's some information there about which horizons tend to be where most of the water comes in. So if you can work out effectively what the elevation of those things is, you can then compare it with this elevation, the reference elevation of the base of the New Haven chalk, and you can sort of express it effectively as a stratigraphic elevation relative to that base. So on the left here, we found 202 points in total. And on the left, I've plotted them relative to that New Haven chalk, base of the New Haven chalk. And on the right, they're plotted relative to ground level. So obviously a lot of these points are based on the sort of superficial occurrence of springs and things like that. So there's a lot of points at ground level. But interestingly, there's still a fair distribution, you know, all the way down to reasonable depths. Some of the public water supply boreholes are at least 130 meters deep. So and in some of those, they get flow into fractures at towards the bottom of the borehole as well. So quite an even distribution really through the chalk, and stratigraphically speaking as well, whilst there are some horizons that we have effectively picked out and modelled because they seem to be more frequently associated with flowing features, it's fair to say that actually the chalk has these either marl or hardground horizons throughout the whole stack of the sequence, particularly around the Seaford and New Haven and down to the Lewis chalk, I would say. So we've taken a selection of these. We can't build a model that's explicitly representing them all because that would be crazily big, etc. But we've taken ones that are particularly important for some of the public water supply boreholes and that basically provide us with a good distribution across the sequence of where these flowing horizons might be. They are things that Rory himself has often seen in the field. So in particular, the Whittaker's 3-inch flint, which is this one, the Seven Sisters flint, which seems to be quite important for many of the areas of the model. You can see here this whole business of, particularly in the unsaturated zone, you often see it in cuttings. The existence of these large cavities representing sort of previous flowing horizons sitting on top of, you know, and promoting preferential flow down the top of these flint horizons. Some marls, and one of the marls at the bottom is what we've picked. And so for each of those horizons then, because we know their relative elevation relative to the New Haven chalk, roughly from Rory's regional correlations, we can say these features that we've picked out are probably on that horizon. And this picture here is the elevation of what that, in this case, the Whittaker's 3-inch flint might be. Of course, that doesn't mean to say it's necessarily hydrogeologically significant everywhere because, well, firstly, it's actually eroded out. All the white bits, it isn't there at all because it's gone. But secondly, it may well spend most of its time in the unsaturated zone above where the water table is and where it's fluctuating. So on top of that, I've put another map here, which is colouring basically, if you take the difference in elevation between the minimum water level and this horizon, then, you know, how deeply saturated is this? So if it doesn't appear on this at all, then it's dry virtually all the time. If you're getting these grey colours, it means that in between the minimum and the maximum water level, it maybe wets up and then dries. And that's certainly a feature over here on the Bourne, possibly for the Whitway Rock, which helps to explain why this river loses a lot of water in the winter down towards here, which is a sink line. And then as it gets deeper, you know, you can see this horizon clearly exists here to the north and to the south, but it's just dipping off to depth. And I've deliberately coloured these things a sort of blue colour, as in they're probably important for flow, only down to a depth of maybe 20, 30 metres below the water table, because if the thing is just resolutely dipping off towards the south, the water, it may be a preferential flow horizon, but the water's got nowhere to go. So these things are only important for promoting flow if there's a sort of way into them and then some sort of discharge route out of them. So these are the likely areas where they may be sort of significantly contributing to flow. The next one down, the Seven Sisters Flint, Again, this is probably quite important, I think, for a lot of things around the Candover stream here, and the headwaters of the River Itchen, and across here. Moving on down, the things get deeper, and I think as soon as they get more than 40-50 meters below the ground, below the water table, they're probably not so important anymore. And the last one that we've explicitly included, because it is sort of a flowing horizon into boreholes, both ends of the sort of the basin, if you like, in the lower stratigraphy, is the new pit or gun garden marl at the bottom. So we've built all of those explicitly into the model. When you look at river flows as well, what you find is that the existence of this structure has a big bearing on the groundwater divide that particularly divides groundwater flow, recharge landing on the chalk in this area, might either trundle off towards the Thames, or it might, and it does effectively much more trundle off towards the Itchen. And the reason for that, the topographic divide is actually here down this line, but you can see from the structure that the dip of the chalk is saying, don't go that way, go west. And because of that, what we find, if we look at some of these headwater gauges, so I'm going to show you the Arl, the Cheriton, the Candover, the Wey and the Caker. If you divide their flow by their surface catchment area, you'll see big contrasts which sort of reflect how reliable and resilient the flows in the Itchen are because of this additional amount of water it's pinching from the Thames catchment, essentially. And then we'll have a quick look at other gauges that are sort of down the bottom of these river systems, both comparing the Itchen and the Test, and also some of these lower gauges on the rivers flowing towards the Thames. So remember this bit here, the Arl, you know, these are a time series plot just for a few years of gauge flows. And all I've done is I've divided those by their surface catchment area, which really picks apart how resilient the flows in the Arl are compared to particularly piddly streams like the Caker, which is one of these little ones that comes off here. These scarp slope springs and streams, you know, the flow is much less reliable, much more seasonally variable in the Caker and the Wey, compared to this sort of really resilient base flow from a much bigger groundwater catchment for the Arl. And the Candover and the Cheriton are sort of in between. And that main Arl tributary to the Itchen makes a big difference to the resilience of the Itchen relative to the Test even. So, you know, perhaps the Itchen is partly special and certainly more resilient in many droughts, I think, than you might expect for a chalk river, partly because it is fed by that, just naturally by that much larger groundwater catchment. So that's a quick look at some river flow understanding. We've also obviously looked, there's an awful lot of groundwater level hydrographs that have been recorded over the years. Some of these, apart from, you know, giving you again this general understanding that the catchment, the groundwater catchment to the Itchen goes right up to the edge of the outcrop here. The time series from these are also helpful in understanding recharge responses, and some of these particularly have data loggers that have been installed so you can understand things on a slightly more frequent basis. These red ones show a lot of quite peaky sort of responses, and I'll show you that in a minute. Over in the confined zone, you've got hydrographs that show a much more sort of sluggish response to both confined groundwater abstraction in the chalk basin, the London basin, and also indicate there is some flow, you know, off from the chalk towards the north in that, much less so towards the south, I think. So just picking out some of these ones that I've circled and plotting them in two ways first. I mean, the first thing to say is that you can see the difference between these peaky ones. So this is just in meters AOD, all of them on one axis. You can see the difference between that and the much more sort of sluggish confined responses in the greys and the blacks down here. The main thing I wanted to pull out though was that if I change this plot and instead of plotting it by meters AOD, if you plot it by meters below ground level, so effectively all I've done for two particular periods is I've put the ground level at the top and I've said, well, where would these water levels be in relation to the ground? Now, the fascinating thing I think here is that there are lots of places in this catchment where there are some very big unsaturated depths. This one down here, for example, you know, 60, 70 meters of unsaturated chalk between the surface at the top here and the groundwater table at the bottom. But you look at that sort of response here across all of that thickness of unsaturated chalk, and it's almost instantaneous all the way down. So what we do find is that there's very little evidence in this area of any real delay in terms of water turning up as rainfall and recharge at the surface and making it to the water table down below. So very rapid. You know, the indication is that the unsaturated zone, which you can imagine has been left behind by the water table over centuries and millennia of dissolution, is like a sort of Swiss cheese that just passes the water down to the saturated aquifer very quickly. And the superficial, so this is just the solid geology map, but the superficial maps are also really helpful for understanding things. So firstly, this is clay with flints. So the clay with flints sits as that kind of residual weathering deposit from the lower London tertiaries around the upper bits. So you can see where the chalk is dipping off underneath the, I'll just ignore that, where it's dipping off underneath the London clay. It's you get clay with flints, and you get on these high interfluves as well, clay with flints. They don't tend to generate much runoff, maybe locally to swallow holes. You find some solution features where there's lots of sandier lower London tertiary material that's made its way down into the unsaturated zone as well. Clay with flints, and then the valley head deposits, fascinating to see. Although if you typically look at a map of chalk rivers, there's no surface water other than the main rivers and a few winterbournes. This sort of map suggests that, you know, back during the glaciation period, Paul Younger has written papers about this, that that many of these valleys, which are now dry valleys effectively, were sort of defrosted talics, as he called them, where there was flow of groundwater in the shallow ground along a lot of effectively topographically defined areas. So often, if you want to understand zones of potential preferential connection, they may be along these dry valley talics, even though they're not reflected by the current drainage patterns. And the last thing I'm just highlighting from the drift deposits are the alluvium, which is obviously more modern. And I've already said previously that the kind of place where you turn from, you tend to get alluvium after you get reasonable sorting, perennial flow in streams, and obviously the main river valleys. So the transition from valley head to alluvium is typically around where there are groundwater springs. So that's helped us in kind of defining that geological structure of those flowing horizons too. As I said, this is another unsaturated zone picture, actually from the Twyford down cutting, you know, pretty Swiss cheesy in its in the unsaturated zone. Looking at the structure again with a cross-section line going from north to south and down the Candover stream here, we'll look at two bits in detail. This bit first, which is along the Candover stream, and then this bit. So looking at this bit and sort of unpacking that a bit, again, what we find in understanding the distribution of flow as this initially ephemeral winterbourne stream then reaches, flows over a syncline area. But as these flowing horizons are brought back closer to the surface, that's the location over the Stockbridge anticline where you begin to get perennial springs and the start of the perennially flowing River Itchen, which is designated as a sack. And probably something to do with faulting further down that maybe allows connection of deeper flowing horizons, which maybe have carried flow like a kind of underpass mechanism, and then return it to the surface where you get some more artesian flow at fob down. So again, structure important, and the folding and things helps to explain where the distribution of the flows are. Looking at a more interfluve area, sort of between the top of the Candover and over towards Basingstoke. This is the structure again, some high bits, turning that into a more conceptually looking picture. The sort of thing that we've been talking about is that you get the clay with flints along the top where as a residual weathering deposit. You can imagine that recharge is trickling down. The whole of the unsaturated zone above the water table is Swiss cheesy, and therefore you've probably got development. You have to have development of vertical features, fractures, as well as these flowing horizons. but probably the recharge kind of zigzags its way down. Again, following dip a little bit in the unsaturated zone, so that there tends to be a divergence maybe of recharge away from these anticline areas, and certainly a convergence towards the synclines. It's probably more marked in other parts of the chalk in North Kent, but it's probably going on a little bit here as well. When it reaches the saturated groundwater system, it's gone through a lot of unsaturated zone in terms of saturating itself with calcite through these high unsaturated thicknesses. So often you find on some of these anticline areas, groundwater mounds, that the interfluve groundwater level that you might expect to be going up and down a lot actually doesn't, because some of the recharge has been diverted away from it, and it's just sitting on a relatively low transmissivity lump of chalk, which isn't that well developed. Towards the synclines, however, the flow in these flowing horizons continues to develop transmissivity and chuck it down the plunge of the syncline, if that's taking it towards some way of getting out of the whole aquifer again. So preferential development in syncline areas, and also the notion of, with the Paleogene and the development of sort of defrosted talics in sort of shallower dry valley areas, winterbourne areas, again, deeper development of chalk transmissivity in those areas. So summarizing all of that in terms of an overall conceptual timeline for the development of the chalk groundwater system, we've got time at the top first. So obviously it was deposited in the Cretaceous. Stuff that went on in the tertiary and the sort of interglacial, pre-interglacial, post-glacial periods and the Anthropocene, all of these have influenced how the aquifer has developed, with deposition, uplift, folding, fracturing, faulting, and then the whole business of you only get permeability in the chalk if you dissolve it. So patterns of rainfall, recharge, weathering, dissolution, both through times of warm climates, through the peri-glacial periods when probably you have permafrost and these defrosted talics, and then the continued development of the chalk in recent times. And then what we've done to it in terms of development of abstractions, water cress beds have been really important. Public water supply boreholes obviously are peppered across the place. Also drainage cuttings, engineering, putting water back in the river, sewage treatment works. So, the fact that the environment in which it was deposited was so low energy, the existence of these silicified sponges and flints, volcanic clay marls, all of those things are going to pan out and help explain distribution of flow, because they've been uplifted and perhaps preferentially fractured and are encouraging down dip flow. And then, the topography that results of that helps to sort of possibly reflect the underlying structure, and also clay with flints, the unsaturated behavior, etc. All of these things are helping to explain why groundwater flow is going the way it's going. And clearly, if people then come along and do cress beds where they enhance the amount of flow coming out of a cress bed, which may originally just have been a natural spring flow, they'll go and pop lots of boreholes in. Howard Hedworth did a lot of work in the Arl cress beds, which are a big centre of flow, and demonstrates that really has also encouraged more flow from those flowing horizons to come out to the surface. Very, very hard to then stop that effectively. And we'll talk a little bit about the drawdown and how that relates to the way that abstractions impact on river flows towards the end. Okay, so we're now onto the bit of the talk where I'm going to say, having sort of introduced the conceptual sort of picture of how the system works, we have sort of recently rebuilt what was originally a regularly gridded ModFlow 96 model. We've made it into one of these fancy kind of Voronoi polygon things, a ModFlow 6 model, and with a 4R model on top, and I'll explain what those mean in a minute. But what the first sort of task when you build one of these funny unstructured grid models is to decide what your grid should be. So series of slides just saying, we know that the main focus really is on the main outcrop of the chalk. As you get into the confined areas on both ends, we're sort of slightly less interested in it, so the model nodes can be a bit bigger. And obviously in the underlying areas, the galt clay, etc., we're not really interested in that at all. So again, bigger nodes is fine. We've got the notion that some of these rivers are going to be part of this core model area. This is the model where, if you want to know what's going on with flows, what they would naturally be, what they would be on the influence of abstractions, etc., come to this model. Well, that's going to be, you know, the Test, the Itchen, some of the chalk headwaters of these Thames streams. But we'll include some representation of other rivers that are actually kind of owned by other models, because we need them in there to get the boundary conditions and the flows right. There are then some receptors, some particular receptors, so that the rivers themselves are a key receptor. They're the main receptor really, but also there are wetlands, valley plain, floodplain wetlands in a number of areas that, again, we've just given a little bit of extra refinement to in the model for future work on kind of how abstractions may be impacting those wetland features. This, by the way, is just a little blur version of this bit down here, so you can see how it pans out on a smaller scale. There are then clearly the groundwater abstractions, and a lot of the questions relate to what are the impacts of these things on those receptors. So we refine the model down a bit so that it can get a little bit closer to radial flow to the boreholes and stuff. And there are a lot of places you've seen already where groundwater levels are observed. So one of the things you can do in Mod Flow 6 is just center the nodes on those. So we don't make the nodes any smaller, but we just center the node so that you know that you're getting a number that's relevant for that location. So those are the main things that go into the grid, and then you stir it up in a package, and you probably have a lot of iteration with your stakeholders, and people argue a bit about whether they want a bit more here or there. But at the end of the day, you end up with this rather lovely soap bubbly thing, which has more focus flow, where sort of there's concentrated groundwater flow in the valleys around the abstractions and around the main receptors. So, and you can see how that pans out in that sort of little bit of detail there. So that's the structure of the model for the groundwater calculations. But it's also important to have the surface water system represented on top of that, which is done in a code called 4R. And that includes a complete routing of the surface water system. So these connections are all saying, when we do a simulation of flow in the rivers, we're going to pass the flow from this one to that one to that one downstream. And we're going to take account of both places where there are discharges, surface water discharges, and these ones tend to be related to the groundwater abstractions that are related to cress beds and fish farms, but also some largish surface water abstractions at the bottom of both the rivers Test and Itchen, which are kind of important influences on total flow in the river, and therefore it's important to include them in the simulation. So the surface component of the model goes on top of that groundwater Voronoi grid. The 4R model then does calculations of runoff and recharge based on inputs of rainfall and potential evaporation, which are going on a daily basis. So this is rapid runoff, so most of the catchment, no runoff at all, only in the really close vicinity of the rivers. Interflow, which is a sort of slightly slower, having gone through the soil moisture deficit, how much water again is coming back into the surface water drainage system, more from the upper greensand, more obviously on the London clay. And the main outcrop of the chalk is dominated by recharge, higher values over the higher ground. And you combine all of those together and you get a kind of total effective rainfall map. So all of that is put into the mod flow model, which has a structure that's sort of reflecting these flowing horizons that I was telling you about. So in this case, it's a 10-layer model with some explicit representation of some of these horizons, just to try to get that bedding parallel anisotropy behavior going in the modeling. And this is a kind of cross section through the modeling east-west and north-south. Sorry, that's east-west, that's north-south. We've included basically the top layer of the model is where most of the water table action is. So above there is sort of unsaturated, and below there you've got potential connections that are made by these flowing horizons, and you parameterize all of that up. So to then worry about the parameters, we've built in, so this is a transmissivity map, we've built in some sort of superhighway really connections which we've done through just looking at calibration between groundwater levels and river flows and trying to get the whole thing to work. And we'll often look when we do this at those superficial geology maps. So looking at this area in particular, you can see here some of these things are related to structure. So that really high transmissivity sort of syncline enhanced sort of superhighway from the Thames into Thames catchment anyway into the Arl is there. Looking at this one here, this is an interesting one. So the Candover would normally come down, well, does come down here as a stream. But if you look in this patch at some of the detailed representation from the geology mapping of where head deposits are, it suggests really that in peri-glacial times that this anticline probably acted as some sort of deflector and took some of the water that is now flowing down the upper reaches of the Candover and sort of deflects it over into this dry valley system and then brings it down to the Itchen further downstream. And interestingly, I found out, so we know for a fact that there's lots of stream flow, spring flow here, where these horizons are brought back up to the surface. But I learned the other day that indeed in the rather suspiciously named Springvale, which is a part of North Winchester over here, apparently that is also very prone to groundwater flooding. And that's kind of at the bottom end of this system. So that was quite interesting. Looking at this patch up here in a bit more detail, this is where this all looks very complicated, but we've had to get the groundwater levels right up here and the sort of spring flows working down here. We've had to introduce some connections that are within these flowing horizons, taking water that is kind of being underdrained from the catchment and not just flowing sort of as it might normally flow towards the nearest bit of drainage, but sort of making its way down to particular outflows that are sort of spring enhanced. Very little bit about model calibration. So after you build this model, you have to check it against the groundwater levels that are sort of monitored across the patch. This is just green blobs mean that we've got the groundwater levels on average within a meter. It's generally not bad for groundwater level calibration. The overall kind of modeled levels for each thing and the observed levels for each thing has got, it's quite a tight sort of correlation, which is good. That's just one example of a groundwater level from one of them. There are hundreds of the blooming things. You also have to obviously worry about river flows, and there are a number of gauging stations. And again, these are coloured up as to green ones basically mean that the average flow is within plus or minus 10%, and it's generally not bad. We'll have a look at 3 gauges going up the Itchen, so from Albrook and Highbridge at the bottom to Boroughbridge at the bottom of the Candover, and then we'll just look going up this sort of Dickier Winterbourne thing, because you have to get the flows right locally in the Winterbournes as well as the sort of bigger overall catchment flows. So from the bottom, you can see high flows are a little bit too high. This is a flow duration curve indication of comparisons between things. And you can see here in the time series that, but the low flows are pretty well represented, which is often the focus of these jobs because of the focus on low flow groundwater abstraction impacts. Moving up to the Candover again, it's a similar pattern. Low flow is pretty good, higher flow is still a little bit too high. And if you go beyond that gauge and look at the whole kind of Winterbourne reach, at the very top, the model is only simulating flow once in a blue moon, and that sort of reflects observations that it's mostly dry. And as you work your way down, people's observations of when it's flowing or not, or what the flows are reasonably represented until you get down to the sort of perennial head down here where it's flowing for most of the time. So it's not a bad model. We're going to have a quick look at this particular patch here, sort of focusing on groundwater abstraction impacts, and just as a bit of a kind of thought thing, really. So 2 things that we focused on a lot have been source A, which is quite a big source. So this is pumping water out of the ground at 11 megalitres a day, all the time in a steady state sort of way, pretty much to provide base load public water supply. Source B, again, pretty steady, 2-3 megalitres a day, something like that. I'm not going to talk much about source B. It's located right next to the Candover. Most of its impacts are indeed on the Candover. There's not a lot of mystery with it. Some of the low flow drought period impacts are less than the amount it pumps for reasons that are similar that we'll sort of introduce with source A. But going to focus on source A. So where is it having its impacts? You know, given the things we've said about the groundwater catchments, the fact that natural flows in the way are much lower, the Arl is there, the Candover and the Diva, those are the main receptors. So the first plot I've put on here is for, if you look at the map bottom right, this basically says this is a plot for the Candover. So we've got one of these for each of these other receptors. There's a time series plot over here, which shows for a sort of low flow, well, a variable flow period between 1990 and 1998. What difference, sorry, does that abstraction make to flow in the Candover at Borough Bridge? And basically what this is showing is that during high flow periods, it has more impact on the Candover at Borough Bridge than it does during low drought periods like here. And in a flow duration curve sort of plot sense, what that means with these flow duration curves is that on the right hand side you have the condition where the flow is exceeded for 100% of the time. So that's where your droughts are on the right side. And on the left side, you've got your floods, which is, you know, the flows that are never exceeded 0% of the time. So summarizing that time series behavior of groundwater abstraction impacts in a flow duration curve impact thing, where effectively natural is across the top, and this is the impact of that source on that receptor. You can see there's a terrific range of between not very much when the whole system is in drought or summers, and much more when the system is flowing a lot. Now remember, this source doesn't change its abstraction rate, but effectively the aquifer is changing that constant abstraction rate into a very variable impact pattern. The other thing, just briefly to say, because there's lots of uncertainty about how transmissivity might actually be distributed through the ground. So the reason why there's many lines on this, or 6 or 7 anyway, is because we've taken several alternative models of things that we're less sure about the transmissivity distribution, and we've asked the same question for each of these models. If you switch that source off, or if you switch it on, what are its patterns of impact? And I guess an interesting conclusion from this is that although there is variability, a lot of, you know, the basic pattern is the same, and a lot of that relates to the structure of the chalk and the elevation of the drainage, as you'll see in a minute. So very variable to the Candover. Looking at exactly the same formats for Bransbury on the Diva over here, much less variable, but also much less. Generally, this is quite far away. Not a lot of variability there. Huge variability for the Wey. So remember, the Wey was a river that you saw previously where the gauge flows sort of almost drop away to nothing in the summer. And that is reflecting the natural behavior of the Wey. If without any abstraction, there wouldn't be much flow in the Wey anyway in the summer. And so it's not surprising that although this source has a constant rate of abstraction, in terms of impacts on the Wey, it's hugely variable between almost nothing and quite a lot when groundwater levels are higher. The Arl flows are much steadier, so there's less of a gradient between high and low flows here, but again, slightly less. And summarizing all of those together, so these receptors, the Wey, the Arl, the Candover and the Diva in these colors, these are the graphs that I've shown you previously. Remind you again, it's a constant rate of abstraction, and adding these things up, you end up with something that says, well, it's about 3 megalitres a day if you add them all up at low flows, and it goes up to 18 megalitres a day, much more than the rate of abstraction during high flow and high groundwater level conditions. So why is that? What's going on here in this headwater area? And the clue is when you look at the drawdown. So if you look at the drawdown in the chalk, which is the difference in groundwater level that particular abstraction is making, this is a sort of map that if you show people, they will often be very alarmed by. They will say, blimey, look at the impact of that source. It's spreading all over the place. It must be a disaster. Let's switch it off. In this case, though, there is no wetland anywhere near here. This is an area where the unsaturated depth is already very big. And effectively, what's happening is that drawdown is a good thing because it just represents that the source is drawing on groundwater storage. So it's developing groundwater storage, drilling a hole in the water table during dry periods, which then gets filled up when it rains in the next wet period. And that's the time that you have the impact. You offset the impacts to the wet periods. And it's kind of almost like you've got a surface water reservoir, because that's what you build surface water reservoirs to do as well. but you don't have to build a surface water reservoir, which is a good job because it would leak because it's the chalk. There's already a really good reservoir in the ground already. So people have known about this patch of ground for a long time. So in the 1970s, not far away from Soley, they developed the Candover augmentation scheme boreholes in this area here. And what this was designed to do was to take flow out of the ground during dry periods and droughts. And in a drought, perhaps, this is being reconfigured at the moment to put the water in the Itchen. Originally, this was put in the Candover, which was not an environmentally friendly thing to do, because the Candover has lots of sensitive ecology, white glug crayfish and things. And if you put 22 megalitres a day in something that shouldn't have that much water in it in the summer, it blasts the ecology out and it's a bad thing to do. So, for that reason, this is currently being reconfigured to put the water in downstream of where there is a slug of water already coming in from the Arl. But the notion here is that during droughts, you can operate this as a drought scheme to basically enhance the amount of water that you can re-abstract downstream by maybe 22 megalitres a day. The scheme also has the capability to keep the Candover flows close to natural at all times. So you can put a much smaller and more sort of environmentally sympathetic variable rate of support into that Candover stream and keep the flows close to natural at all times. So adding up those numbers, you've got source A 11, 3, 22, up to 4. That's about, during a drought, that's saying this patch of ground is giving you maybe 40 megalitres a day of water into supply. And because of the operation of this augmentation scheme, it's also actually supporting flows down the Candover stream and down the River Itchen during summers or indeed severe droughts, which is kind of a good thing for the ecology in terms of ecological outcomes. It means that you're close to natural flows most of the time. However, this is under challenge, and this is where we're moving towards the last 10 minutes of the talk, really, to say things look like they're going to change on this patch of ground, or could at least potentially change. The main accusation really is none of this is natural. It's just not natural to have an augmentation scheme which kind of looks like it's a bit of a sticking plaster on the impacts of these things. And therefore, what should happen instead is that all of this lot, under the Environmental Ambition Challenge and under the sort of objectives that Natural England has set for the SSSI reaches of this Itchen Sack River, which also, by the way, applied to the Test and to the Avon and lots of other rivers as well. So under those, the mantra is you need to achieve close to natural conditions for the environment, for those gin, clear, fish jumping waters, but you can only do that naturally. So you can't support the river artificially at all. The consequence of that, if that does pan out and works its way through over the next 20 years, is that we've lost all of that 40 megalitres a day, because you'd have to switch off source A, source B, and the Candover augmentation scheme. And furthermore, at the bottom of the catchment, there are some large surface water abstractions and groundwater abstractions at the bottom of the catchment. Again, you need to lose a further 40 megalitres a day from the Itchen pumping in order to meet the conditions that Natural England have set for this river. So summarising, adding together 40 and 40, you get to 80 megalitres a day. So there seems to be a serious plan, or a desire at least, to reduce abstraction in this patch by 80 megalitres a day. Now, obviously, for public supply, you need to find that from somewhere else. And the somewhere else turns out to be only things like effluent recycling, very high treatment costs, possibly desalination, again, high treatment costs, maybe making links with perhaps a new reservoir that will be built in Thames, perhaps. And all of those things themselves obviously have their own environmental impacts. They're not local to supply. They will involve huge capital costs. So, at the moment, this patch in the Itchen in total, maybe you're looking at between 200 and 300 million quid to actually find those replacement supplies that you maybe develop over the next 20 years. Somebody's going to have to pay for that. And, you know, at the moment, customers are obviously paying a lot more for gas and everything else. So to what extent can you really realistically put lots more cost on customers' bills? And once you've even got them in place, the notion of operating these sources where you're pumping water from much further away, you're having treatment, there's a lot more carbon involved. So again, lots of both carbon and financial costs in the operations compared to the existing system, which is local sources, local water for local people. So, and that little bit that I've just done about that corner down here in red of the chalk aquifer is something that this broader Environment Agency environmental ambition challenge to try and meet river flows everywhere, and to do so by reducing chalk abstraction. These blobs on this map are the size of abstraction reductions that are being asked for, roughly. This is actually an early draft map, but so it's not the exact numbers and you can't tell when any of them are, but you can see basically all the blue blobs are public water supply abstractions, and you can see that they roughly map onto both the outcrop of the chalk nationally and also the main sandstone aquifers. So huge amount of water, you know, roughly half to a third reduction in the amount of current water that we're getting from groundwater storage. We'd have to get from somewhere else. Quick look to the future before I go into the last 5 minutes. So what will happen with climate change anyway? We've got 3 hints of that. The first is within the modelling that we've done already between 1970 and 2018. You know, we have to put in the inputs into the model include rainfall. These are annual totals. We have to put potential evaporation, which then calculates actual evaporation, and then you're left with some effective rainfall. In all of these models that we do across the country, we already see that of all of those time series, there's obviously a lot of variation to do with the weather, but actual evaporation has been creeping up over the last 50 years. And that's because temperatures are rising. And with more temperature rising, warmer winters, more water is going to evaporate. So flows are going to go down. And looking at, so these are formats that I've taken from a new product that's come out effectively based on the UK CP18 climate change projections called eFlag. And it's basically the update of the future flows data that was previously produced for UK CP09. This is for one of the tributary streams at the top of the Itchen. It's not based on our modelling, it's based on their hydrological PDM modelling. But what these traces are showing is rolling averages of 18-year different flow percentiles. So going from Q99, very low flows, kind of droughts, up to Q1, the highest flow floods. And basically rolling that 18 years forward and looking at that percentile across 12 equally likely climate projections. What this suggests, which again is a familiar story, is that the very highest flood flows we can expect, there will be probably over the century, and this is going from 2000 up to 2080. And over here, you've just got an account of how many of these models are falling in different change buckets in terms of percentages. So here, the fact that you're seeing some blue means that, you know, maybe at least 6 or 7 out of the 12 models are suggesting that there will be increases of more than 10% in the highest Q1 flows. So that's basically more stormy runoff and rainfall. So there will be some higher flow events coming in. But as soon as you get down even to median flows, you're finding that the overwhelming majority of models are suggesting reductions in what flow will be experienced in the Cheriton stream and indeed the Itchen and across the region. Down at low flows, the bulk of these models are suggesting you might have reductions in over around 20% of what the Q95 numbers are, bearing in mind the current sort of estimates of the current constraints to do with these flow targets are more like 10%. So river flows are going to change significantly. And that's sort of even more the case at the low flow end of things. So we can understand why there is this challenge to think about what we do. But I would question whether the right thing to do in the face of a drying climate is to give up your groundwater sources, which are reliable, resilient. I don't think any other countries would do something similar. We have also considered much more severe events. So we've done some modelling. This is flows in the River Itchen of drought flows. And there are some historical events, 1973, 1976, 91, 92. The water companies are being asked to plan for 1 in 500-year events and 1 in 200-year events. And you can see the flows that you can expect in those droughts are significantly lower. So, you know, it's right that we need to be planning for supply resilience and indeed environmental resilience through those much more significant events. A picture that Stuart Allen of the agency put up, this is an example of this is the River Thames actually. You know, droughts are serious things. They result in fish kills, they result in environmental damage really. They're natural things, but they're not good for the environment. And just to sort of slay another myth, hopefully, there's a lot of talk at the moment about natural flood measures, you know, things you can do to catchments. And I'm just sort of making it clear that there's no sort of nature-based water retention or land or soil restoration measures that will turn that into that. So, you know, 5-minute grumpy polemic warning. Do we want to hang the Itchen out to dry is my question. This is a talk I actually gave to some people in Westminster about a year ago. The Environment Agency strapline, water for life and livelihoods, is that where we're at, or are we really just talking about water to meet river flow standards? At this point, I have to disown my company, or they will disown me. I have to apologise to all my beloved clients because I'm going off on one. Environmental ambition is good, but have we lost our balance? We seem to be pursuing river flow standards regardless of what the ecological benefits or costs may be. We are at risk, I think, of abandoning our access to groundwater storage on a large scale, and I think we really need it. If you were to ask Spain, you know, which is a lot drier, what do you depend on? They'll say groundwater sources. We're also seen to be making anything to do with management a dirty word, just because it's just not natural. And I'm seeing around the sort of water wars that I'm beginning to see developed around this narrative, people locally are saying, no, we can manage this wetland, we can scrape it out, we can make it a bit deeper, we can keep it, keep the biodiversity we want, we can create it much more easily than we could by sort of simply reducing abstraction. Abstraction reduction is being prioritized more than land stewardship, habitat creation, etc. And I'm not sure that's wise. So we've come on a journey. I've personally come on a journey from 20 odd years ago or something, when I was helping the agency invent this process of having flow duration curves naturally, that you hung some river flow screening thresholds off and you compared that with what the flows actually were in the river. And if you get this situation where, you know, the actual flows are lower than that, you then go into a sustainability assessment, it was called, where you consider both, you know, the environment, yes, but also people and carbon and pounds. I think what's happening now is that in many places, those green lines have been made red standards. The idea is that they should possibly be tightened. And also the word sustainable has been hijacked by saying this just means meeting the river flow objective. So restoring sustainable abstraction just means meet the river flow objective. And I fear that's setting us up for a future where low flows are going to go down. You know, we're still going to find that we're going to have disappointed environmentalists and we'll have spent a lot of money on the way. So previous calculations that we've done, you know, we produce maps that have red and orange and yellow bits showing where we're not meeting the river flow standards. And now we're saying we just want to raise the standards and meet them everywhere and turn the whole map green. The consequence of that is mostly related to reduced groundwater abstraction. You know, nationally, maybe 6,200, possibly reduced by 2,700. You know, that's eye-watering sums of money to something that would get the map closer to green. And we're replacing sort of local water for local people with distant, more expensive operational costs. So the sort of options that water companies consider in their planning, I'm sorry, I know I'm 2 minutes late, but I will finish in 2 minutes, is things that are still, you know, leakage reduction, demand reduction, everybody knows they're good things, they will continue. But some of these other smarter options like groundwater augmentation, etc., they're still on, but a lot of these in the middle, you know, we're now talking about new reservoirs, desalination, etc., but these ones are just not natural. We're being told to stop fiddling about. And I fear that's going to set us up for a future of some massive engineering, which, you know, we're still going to end up with dead fish because we haven't got the wherewithal to support the river flows because we've turned up our augmentation schemes. Punchlines, last slide. So really what I'm saying is I don't think I think the word sustainability has been hijacked. It's not about just meeting river flow objectives. It also includes carbon, biodiversity benefits and costs. I think this mantra that you have to get to natural river flows and you can only do so by switching off groundwater abstractions, that's a really dangerous sort of turning our back on these national assets, really, at a time when during these future droughts, we're going to need that water to keep us going, supplies, and also to keep the environment going. I think we should have more focus on the sort of things, I'm all for rewilding and catchment wide stuff. Don't expect it to change the flows much, but it's absolutely vital because those are the quicker, cheaper, better way of realizing ecological outcomes. And, frankly, if we get to this situation where all of those abstractions have been switched off, why do you need to study the chalk anymore? So, to a certain extent, from a selfish point of view, I'm saying hydrogeologists unite. And that's it. Thank you. I will stop my sharing so I can see if anybody has any questions. Sorry, I went on for 5